This is Cycle 1, Lesson 8, and we're going to continue with rational functions. In particular, today we're looking at solving rational equations and inequalities, and of course we're going to do it by graphing, as we will do most things in Cycle 1. So let's start with something that we're a bit more familiar with, which is the equations, and then so the first couple of examples we're going to look at solving equations, then we're going to go on to solving inequalities after we've become masters of the equations. We've already done this. We've already done this for polynomial functions, so we're going to use some similar kinds of techniques to help us do it here. So method A. All right, we can, if we've got this rational function here, rational equation here, what I can do is I can graph each side of the equation separately in Desmos as a separate function. So in other words, the left side of the equation, let's think of that as one function, and then the right side of the equation I'm going to think of as a different function. Let's make this one green, and let's do the right side. Let's make that one blue. Okay, and then let's go to Desmos and see what those look like. Save a little time, I've already put them in here, except the color doesn't match. Let's make this color different. Let's make this one green. Okay, so here's the first function, y equals 4 over x minus 5. Okay, great. So it's a rational function. We've already seen how rational functions work a little bit. We can see that it's got a vertical asymptote at x equals 5 and a horizontal asymptote at the x-axis. Now this one I wanted to make blue, so let's do that and turn it on. And again, we can see what this function looks like. It's got a vertical asymptote at x equals -4, which we would predict from the denominator of the equation. It's actually got a horizontal asymptote at y equals 2, and that's because of the +2. Everything's been shifted up. It's been transformed up a little bit. Anyway, so we got these two functions. We graph them, okay, in Desmos as a separate function. Then it says we want to see where they intersect. Okay, no problem. I'll just turn the green one on, and we got actually 2 points of intersection. At 7.306 is the x value, and then there's a y value associated with it, but I only care about the x values, and -2.806. So those are the x values of where they intersect. So for those x values, let's focus on the -2.8 one. If I put -2.8 into the green function, I will get a y value of -0.512. But if I put it in the blue function, I get the exact same value, -0.512 on the blue function as well. That's why it's the point of intersection. So those two functions are equal at the point of intersection as far as the y value output goes. So those are our solutions for this first part. Okay, so we just go back to our graph, and then we just we go back to our sheet and we write down the values for the point of intersection. So the solutions are x equals -2.806, and that's just Desmos rounds it to 3 decimal places. There probably were more. We could round it to just 2 decimal places if we want to just call it -2.8. In fact, I think I'm going to do that. I'm going to get rid of these other ones. We don't need that much precision for this. And I'll round the other one to 1 decimal place as well, 7.3. Those are the solutions to this equation. And I guess also I was supposed to graph this. So let's just do a quick graph here. All right, so we had a green one. I'll try and again make things color code. So the green one had horizontal asymptote, it had a vertical asymptote at 5, all right? So I'll just draw in my vertical asymptote. It's good to see what the sketch looks like. I want you to see it here. So it's got that vertical asymptote, it's got a horizontal asymptote at the x-axis, and it just sort of comes down like this, roughly, right? This is a sketch. We don't have to be precise. This other one comes across sort of like this, and then goes down so that it looks like this without touching the asymptote again. The blue one, all right, that one had a horizontal asymptote at 2, again because it was moved up a little bit. It had a vertical asymptote at -4. And so we had one part of the graph that looked like this. And another part of the graph that looked like this. And again, we had those points of intersection at about -2.8 and supposed to be 7.3. I'm going to make this dot bigger so I can sort of hide the fact that my sketch wasn't perfect. But you get the idea, right? All right, so that's one way of solving well, we can do this with any kind of function. If we got two separate sides, just graph them each part separately and see where they intersect. The other thing we could do is we could move it all to one side, make a single equation out of it. So if we call this, just call it something else, we'll call it h at x, and then we'll have the 4x, equals 4 over x minus 5. And then we'll bring this minus 3x plus 4 over to the other side, so it becomes plus 3x, 3 over x plus 4. And we bring the plus 2 to the other side, it becomes a minus 2. Now we've got a single equation. So I've combined everything in this red box into an equation where it's all over, or a function where it's all on the one side. And so I'm going to graph the whole thing at once. So I've moved all the terms to the left side. I'm going to graph it in Desmos, as it says. But this time I'm going to look for the x-intercepts, because I'm only going to have a single function. So the x-intercepts are what I'm looking for. I guess the reason I should be clear about this when let's see, let's just move this down a little bit. What I should have shown you first, but I'm going to backtrack and do it now, is first, if I just move everything over to one side as an equation, so really what I just backfilled in there is if I took what's in the red box and then moved those two terms, -3 over x plus 4 and positive 2, move those over to the left-hand side, then really the equation just becomes 4 over x minus 5 plus 3 over x plus 4 minus 2 equals 0. So that's the equation rearranged, and then what I've highlighted in purple is the related function, where I've replaced the 0 with h at x. Because now I've introduced two variables, x and h at x, and I can graph it as a relationship. So again, the equation is on the top, and the related function is on the bottom, but I need the function in order to graph it so I can solve it. All right, so I've already got this typed into Desmos. And it's already in purple. Nice, that works for me. Okay, so here's the graph. And what we want is the x-intercept, -2.806 and 7.306. If those numbers seem familiar to you, they should. They were the solution from using method A, the first method for solving this equation. It's the exact same equation, so I should get the same answer even if I'm using a different method for doing it. So in method B, I rearranged it, but I got the exact same answer. And in fact, maybe I'll just copy this as well so I don't have to write it out again. See if I can put that down here. No, that went somewhere else. Oh, that went all the way up there. Well, so much for being lazy. All right, x equals negative 2.8 and x equals 7.3, and I thought I was so clever. All right, and then if I want to see the graph, again, just so that we have something to reference. Now this one's got two vertical asymptotes, both the vertical asymptotes number 4. So we got a vertical asymptote at x equals 5, just like above, and at x equals negative 4, again, just like above. But now instead of having two separate functions, we've got a single function. It's got a, well, it does have, what does it have? It's got a horizontal asymptote at x equals negative 2, although it does cross it, as we're going to see. So here's one section of the graph. And it sort of goes like this. And then we had another section that went like this. And one more section that kind of went like this. So that's what the graph looked like, right? Just to go back to it for a second, there it is. It does have a horizontal asymptote. We'll talk more about horizontal asymptotes later. You can cross them. You can't cross vertical ones, but it is possible to cross a horizontal one. So those two end pieces are actually getting closer and closer to negative 2, as you can see when I zoom out a little bit. That gives us our end behavior, but that's a lesson for another day. All right, so that's two different ways of solving that rational equation. Either graph each part separately and then find the point of intersection, or put them together into a single function and find the x-intercepts. All right, so how can we extend that to a inequality? Because that's what we've got in the next part. Now we've got 2 over x minus 1 is less than or equal to minus 3 over x plus 3. Well, let's start by pretending that it's just an equation. So we're going to pretend that it's just like we did above. So we can graph each part separately. And so again, maybe I go, let's do it in blue. F at x equals 2 over x minus 1. That's the one side. And again, got that typed in there to try and save a little time. Let's make it green though, make everything match. Not black, green. All right, so there's the graph of the one part. And then the other side, do that one in blue. Call it g at x. Negative 3, doesn't matter if I put the minus sign up top. Graph that side in Desmos. Change the color, make it match. Okay, so we got this. We've got these two graphs, and again, if we find the point of intersection, that could be helpful to us. In fact, let's just take a moment and draw a sketch of it, because I think we're going to want to, I want to illustrate some stuff on the sketch more for this one even than for the first page. So for the first one, we've got a vertical asymptote at 2 over x minus 1 has got a vertical asymptote at positive 1 and a horizontal asymptote at the x-axis. So it's going to come down like this. And it's going to have another section that's below the x-axis, and it's going to be like this. The other part, the one that I did in blue, as you can see, goes sort of flipped around. So that one has got a vertical asymptote at -3 and a horizontal asymptote at the x-axis, and that is going to look like this. And then we have the other part. And it's going to look like this. Okay, so we have those two parts. So, all right, we've graphed both of them. I even know what the point of intersection is. There's only one point of intersection, but let's make that clear right now. If we go back to Desmos, it was at -0.6 and -1.25, which that part doesn't matter as much. But -0.6, -1.25 are the coordinates. That's really hard to read, isn't it? Let's do it in a different color and do it in black. -0.6, -1.25. That might be a little easier to read. All right, what we have to do now, though, because it's an inequality, sorry, I want to look at this, is I want to find all the sections of the graph where the first function is below or above the second. Well, which is it, below or above? In this case, I want to find all the parts where the first section is below the second section, and that's simply because I've got the first part is less than or equal to the second part. See, I just highlighted in red that less than sign. So the first section, the first part in green, needs to be less than, below, the second part, the part in blue. So I'm looking for all the parts of the graph where the green graph is lower down than the blue graph. So I'm going to highlight that in red. All right? So we can use asymptotes and points of intersection to divide up the sections of the graph. So the first section is going to be this whole part here up to that first asymptote, that asymptote at x equals -4. Because that's where things get divided up a bit. So up to there, that's one whole section. So for that section I've got highlighted in yellow, is the green graph below or above the blue one? And obviously it's below it. So I'll just outline this in red. This section of the graph, the green graph is less than the blue one. So that part of the graph we want as part of our solution. Then I got another section of the graph from here, from the asymptote over to the point of intersection. Because at points of intersection, they cross each other, right? So that's also an important thing. So for this part, basically all the way up to the top, is the green graph below or above the blue one? Clearly it's above, so I don't need to highlight that or use that part. But then we have another section from this point of intersection over to this asymptote where we can see the green graph is again below the blue graph. So from -0.6 to this asymptote at +1, again, we got the green graph below. And then the last section of the graph is from this asymptote here all the way over to the right. And so forever and ever we can see that the green graph is going to be above the blue one because the green graph never crosses the x-axis, so it can't get below the blue one, which never goes above the x-axis. So these two sections that I've highlighted in red are going to give me my solution. So I want to find the x values that go along with those parts I've highlighted in red. So if I start at the left, I can see basically that this section here goes to -infinity. The x values will go to -infinity, and this section starts at -3, I believe it was. Yes, -3. So anything less than negative 3 is part of my solution. Negative 3, I'm not going to include negative 3. I'm not going to put an equal sign underneath here. I'm not going to do that. Let me get rid of that, because negative 3 is an asymptote, and therefore I'm not going to, it can't be part of my solution. X can't be negative 3. Well, it should be a negative there. Then there's the other red section, which was from negative 0.6 up to positive 1. So again, I'm going to put the x in the middle. I'm going to put negative 0.6 on the left, less than x, less than positive 1. So in other words, x is between negative 0.6 and positive 1. That's this section here. Any value of x between negative 0.6 and positive 1 satisfies the equation. So that's fine. The last thing, though, is, again, I can't include the 1 in my answer because that's a vertical asymptote. But the negative 0.6 can be included. I'm going to include it because I want, the original question wanted any places where 2 over x minus 1 was less than or equal to negative 3 over x plus 3. While at negative 6, negative 0.6, they're equal. So I do need to include that equal to sign in that, under that 1 less than symbol. So putting all that together, that's my full solution. Now method B is to do the exact same thing as I did in method B above. I'm going to combine it into a single function, and instead of looking where one graph is below the other one, I'm just going to look at where the overall graph is below the x-axis. So if we rewrite this as a single function, single equation, let's do that first of all. So 2 over x minus 1 plus 3 over x plus 3 equals 0. So I just brought the negative 3 over x plus 3 to the left-hand side, made it a single equation. Now I'll get the related function, I'll call that h at x. And that's 2 over x minus 1 plus 3 over x plus 3. So there's my related function again. Let's graph it. Okay, here's the graph. Let's take a little time to just draw a sketch of it. So I still have vertical asymptotes. Zoom in a bit. Positive 1, negative 3, horizontal asymptote on the x-axis. And the graph looked like this. For a rough sketch, that's one part. We had another part that looked like this. Something like that. And then we had our last part, which was above the x-axis. Oh darn. Didn't mean to turn that into a line. Let's try that again. Something like that. All right. So there's the graph. It has the x-intercept, negative 0.6. That makes sense because, again, when we make it a single function, we want to see where it crosses the x-axis, and that would be at the same place where when we did it as two separate functions, they intersected each other. And this time, since there's only a single function, all we're looking for is the place where this equation is actually less than or equal to 0. So instead of making that an equal sign, make that a less than sign, less than or equal to 0. So what does it mean for 2 over x minus 1 plus 3 over x plus 3 to be less than or equal to 0? It means anywhere where the graph is below the x-axis or equal to it. In other words, touching it, x-intercept. So this part, and then this part, and we only care about the x values. And again, we saw that this was the x value of negative 0.6, y value 0, it's the x-intercept. So it's going to be the exact same solutions, again, just getting at it a different way. X is less than negative 3, or x is greater than negative 0.6, greater than or equal to negative 0.6, I should say, but less than positive 1.